In the upcoming demo, we'll be working with custom conversions and looking at how we can use pre-convention model configuration to create a conversion that is used on all properties that have a specific type. To implement this, we'll return to the configuration that we did in the previous module where we set up a maximum length on some of the string properties using data annotations. Rather than configuring such a restriction using annotations, we shall instead bulk configure it for all string properties on our entity classes. What we've done so far has been to add a conversion for a specific property on a specific entity. Sometimes we might want to set up the same kind of conversion for all entity properties of a given type. For example, if CraftRock has told us to also implement a status on the orders entity, such as the order status property that we see here, which uses the same status enum as we did for the customer status. In such a case, we would probably also want to set up an enum to string conversion for that property. But rather than simply setting it up once again on the order status property, just like we did for the customer status, we can use pre-convention model mapping to set up a bulk conversion rule on all instances of the status enum on our entities. We do so here in our database context by overriding the configure conventions method. This method gives us access to a configuration builder instance on which we can set up our bulk conversion rule. We do so by calling the properties method on that instance and specifying the status enum as the generic type parameter. This returns to us an instance of the properties configuration builder class on which we can call the have conversion method where we specify the converter that we would like to use as the generic type parameter. This requires us to create a specific value converter class to use for this conversion. And as we can see here, we have specified a class called status converter, which we shall soon take a look at. But first, let's take a look at the code here below. As you may remember from the previous module where we looked at data annotations and the Fluent API, we have already set up max length restrictions on a number of properties in our data model. But for all the remaining string properties, where we haven't set anything up, if_call will infer that they should be mapped to an invarchar type of size max. This may not be what we want, since it could lead to poor performance and our database taking up too much space on disk. So to handle all these cases, where nothing else has been specified, we've created a converter called short string converter. And here we set up that it should be applied to all string properties on all our entities. This will not override settings that we've explicitly made using annotations or the Fluent API, but it will apply in all those cases where we haven't made an explicit decision. So let's head over to the converters file, where we have defined these two new converter classes. The first one that we see here is the status converter class. The class itself simply consists of a constructor that calls the base class constructor, sending in two expressions that look very familiar. This bit of code that we see here is exactly the same code that we used when we set up a value converter in our database context, and which will now be used by if_call for all entities that have properties of the status enum type. The class that we see below here is the short string converter class, which creates a conversion from a string to a string. This might seem counterintuitive, but remember that what we wanted to achieve was not to change the type of the data, but rather to set a max length restriction on it. We achieve this by simply letting the two expressions return the data unchanged, but also adding a third parameter to the call to the base constructor. This overload of the constructor accepts an instance of the converter mapping hints class, and in the code here we create an instance of that class, passing in the optional size parameter to its constructor. This class takes a number of optional parameters as input to its constructor, which we can use to specify size, precision, and scale of our properties, and whether or not our data should support Unicode. In our case, we used the size parameter to specify that we would like all our string properties to have a max length of 100. And as can be guessed from the name, this is just a hint. So as we just mentioned, this will not override any explicit settings that we've already made. If we now try to create a new migration, we can see how this will be mapped to the database. First of all, we can see that the nickname property on the customers will now be altered to have a max length of 100, changing it from an invarchar max to an invarchar 100 type. Also notice that the order status that we just added to the orders entity is mapped to an invarchar column on the orders table. And here we see that it has been mapped to an invarchar max type. This is because when we set up the conversion of the status type, we did not specify any max length. And it's not being called by the convention that we set up for strings, since this is a conversion from an enum to a string type. We could have changed this by also adding a converter mapping hint to the status converter, but because we did not, the status is mapped to an invarchar max. If we scroll down a bit, we can see that several other string properties are now mapped to invarchar 100, such as the address properties from our own entity type, and also the consumer type property, and so on. So let's apply this to the database. And head over to the Server Explorer and cast a quick glance at the table definition for the customers table. As we can see here, most of the invarchar columns are now of the type invarchar 100, except for the ones such as first and last name and the username, where we explicitly set a max length of 50. We also find the customer status here, which has the type invarchar max, just like we would expect. And if we execute this select statement on the users table, we can see that none of our customers have any status set for them, since we did not provide a default value for this column. So let's head over to the program class in our GUI console application and try setting this value. Do so by using these few lines of code here, which simply first fetches the first customer from the customers collection on the database context, and then sets its customer status to active, and then finally saves the changes to the database. Let's try to run this code. So if we advance the debugger one step, we can see the custom instance here in the watch view. And as we can see, its customer status is pending, as we saw from the select statement that we just executed. This does not come from the database, but is instead the result of the conversion that we set up where we defaulted to the pending status. If we were to call save changes on the database context now, this value would not be saved, since as far as EFCore's change tracker is concerned, this entity is unchanged. But if we advance the debugger step and assign a new value to the customer status property on the customer, the change tracker will notice this, and if we advance one more step and save the changes, we can head over to the Server Explorer and execute the query once again. And as we can see, John Doe now has the active status. In the demo that we just watched, we got an overview of some of the value conversions that we can do using EFCore. We also looked at setting up bulk conversions using pre-convention model configuration. Value conversions is a powerful tool that allows us a very large degree of control over how our real-world models are inferred on the database. And they also allow us to generate .NET native constructs such as enums from strings in the database, which can help make building business logic flows much easier. In this module, we looked at some of the more specialized scenarios that might come up as we map our data model to the database. Some of these scenarios might have been corner cases, such as working with shadow properties and indexer properties, but as we saw, they can have uses for us in certain scenarios, and as we learned, shadow properties are used extensively by the EFCore framework to facilitate a variety of things, such as navigation properties on entities that do not have an explicit foreign key field, temporal tables, and direct many-to-many relationships. All of this takes place behind the scenes, but it is relevant to know about how these things are set up if we want to tap into the information stored in such properties. We also looked at owned entity types and value conversions. Both of these are powerful tools that help us create complex entities that are ideally suited for creating the business logic we need in our .NET applications, and still be able to map these entities to the database in the most optimal way possible. But of course, there are trade-offs. Indexer properties, for example, may at first seem like a low-impact way of expanding our entities and database tables, and also making them configurable from the outside, but they also make accessing these properties more cumbersome, and may cause our code to be more difficult to maintain. The same goes for owned entity types and value conversions. It makes a lot of sense to pay attention to which types you use on the database, as doing so can have a big impact on the performance and the accuracy of the data you store. And of course that also applies to the data types that we use in our .NET code, whose primary objective it is to facilitate the business logic that we want to implement. But it's not always necessary to build the conversions directly into our data model. Some of the things that we've done here in the demos could also have been achieved by converting between simple data model entities that more closely mirrored the database and dedicated business logic entities. That is not to say that these tools are not useful. They are indeed, and for most of us they're indispensable. But when building a large body of code that needs to go into production and to be maintained by several other developers throughout its lifetime, it's always important to keep in mind where we need to preserve flexibility and where it is acceptable, even needed, to use a solution that will be more costly to change. And to wrap things up, here are a few resources that are mentioned throughout the module that might be worth checking out. First of all, there's the Microsoft documentation on indexers that we mentioned when discussing indexer properties. And then there's the Microsoft documentation on shared type entities. I hope you enjoyed this module. In the next one, we'll take a look at mapping database objects. Hi, and welcome to the Mapping Real-World classes in EFCore 6 course. My name is Torben Jensen, and in this module we'll explore how to map database objects. In a relational database such as SQL Server, a database object is a data structure that can be used to store or reference data. In this module, we'll look at some of the more important ones, such as user-defined functions, stored procedures, and more. This module will be all about database objects. We'll be looking at how we can interact with some of SQL Server's programmability features, such as stored procedures and user-defined functions, both of which can be powerful tools for us as we seek to optimize our database performance. We'll also be looking at mapping queries to views using EF Core and how we can set up indexes on our tables. Before we get started, I just wanted to mention that as we are working with stored procedures, user-defined functions, and views throughout this module, we'll be mapping them slightly differently than what we've done so far. This is because as per the latest version of EF Core, there's no support for creating these database objects directly. So instead, we'll be creating them using code-first migrations in a way that we haven't done before. If you'd like a bit of introduction to doing this, I suggest you take a look at Julie Lerman's Entity Framework Course 6 Fundamentals course. Let's start by talking about stored procedures. So a stored procedure is one or more SQL statements that are saved and which can be reused again and again. In fact, they're quite similar to functions in other programming languages such as C#, since they can accept input parameters and are able to return several output parameters to the caller. They can also be used to call other stored procedures and can return a status to the caller to indicate success or failure. There are several reasons why we might be interested in stored procedures, and one of the most common ones is that it's simply a policy decision for certain organizations that some critical queries or even all queries must be executed using stored procedures. There may be a number of practical reasons for doing this, such as attempting to reduce network traffic. By using stored procedures, you are able to send less data across the network connection, because instead of sending all the code that needs to be executed on the database, only the call to execute the stored procedure is sent. And using stored procedures also allow for better security by preventing SQL injection. When we use stored procedures, only the call to actually execute the procedure is sent. The internals of it are invisible to the outside world. This also means that malicious users are not able to use sniffing programs to see table structures and the names of other database objects. Stored procedures can also help us control permissions by allowing us to grant permissions directly to the stored procedure rather than the individuals executing it. And stored procedures also facilitate code reuse on the database level. This might not be a huge issue since the queries we generate in our C# code can also be put into functions, but having it on the database gives another advantage, since the stored procedure is compiled the first time it is executed, and subsequent calls to it will reuse the execution plan that was created during the first execution. Since the query processor does not have to create a new plan, it typically takes less time to process the procedure than running the equivalent SQL as raw SQL. Stored procedures are very flexible and can contain several select statements that contain loops and conditional statements, and they can be used to modify data in one or more tables. Consider for example this very simple query which fetches all orders from the orders table. In the upcoming demo we'll see how we can map this to a stored procedure using EF Core. Mapping stored procedures in EF Core runs a little reverse compared to the other things that we've mapped so far. Since EF Core doesn't directly support configuring a stored procedure, what we'll have to do instead is to create an empty migration and put the code for creating the procedure inside of it. After having done so, we're able to apply it to our database, and then we can call the query using EF Cores from SQL methods. And then we can call the query using EF Cores from SQL methods from SQL Raw or from SQL Interpolated.